2021 question number 6. Another great lesson in making sure that you read the full paper, because there are a lot of very easy marks hidden away at the end of 2021's paper. Very easy indeed, starting with write an equation for the formation of xenon tetrafluoride. So we know that tetrafluoride is going to have 4 fluorines in it. So xenon tetrafluoride is going to be XeF4, and we're going to make that from Xe and F2. Make sure it's balanced. And there you go, 1 mark in the bag. The structure of xenon tetrafluoride has 6 electron pairs, and therefore the structure is based on an octahedral configuration. Draw a dot and cross structure for xenon tetrafluoride. So my Xe, my F, my 4 Fs. Make sure you put all the fluorine electrons in, otherwise it's not going to be valid. Like so. Don't even need to count the electrons because you're given enough information in the question where it says it has 6 electron pairs on xenon and therefore is based on an octahedral configuration. At the moment I've got 1, 2, 3, 4 electron pairs, so I'm just going to put an extra 2 electron pairs. Sort of, I mean, it's a bit messy, right? I guess if you wanted to, you could sort of say, you could do it like that. Oh, does that make it even worse? You know, just make sure that it's clear that, you know, these 2 electron pairs are by themselves. If you're going to draw it with, you don't need to draw dot cross diagrams with circles, but if you are, draw the circles first, otherwise it ends up looking like that. Anyway, that's another easy mark. Then it says draw the 2 possible 3-dimensional arrangements of the electron pairs on xenon in xenon tetrafluoride and tick the one adopted. So this is basic VSEPR. As long as you know your octahedral shapes for VSEPR, you're going to be fine. It does ask you for the 3-dimensional arrangement. So we're going to go with the first one is going to be, you probably should have come across this in class really. So it's the classic 4 bonds but with 6 electron pairs. So it gives, oh, what have I done that for? Let me see. Can I correct that? Yes, I can. Let me just get rid of that. So yeah, so 6 electron pairs with 4 bonds gives you your square planar, and that's the one it's going to be. The other option, the only other geometry it can be, is the if I've got the fluorine there, the fluorine there, fluorine, and fluorine like that, is going to be your other option. And then like that. I guess so you might think there are other options, like for example if I put this fluorine up here and put the lone pair down here, but that's the same. This is the only other way of doing it. These are the 2 options. And square planar is the obvious preference because it has the lone pairs as far away from each other as possible. Then, you know, I feel like that's a very generous 2 marks. You know, it's very, you know, so we've got 4 marks easily in the bag. Can we get another 3 marks? Draw the possible 3-dimensional arrangements of the 5 electron pairs on xenon in xenon difluoride and tick the one adopted. So again, xenon difluoride, it's not even, the thing about this question is you don't even have to work out what the correct number of electron pairs is. It just tells you. It tells you that xenon difluoride has got, well, you know it's got 2 fluorines and it's got 5 electron pairs. So those are I've got 2 from the bonds and then the 3 lone pairs. So there's that one, based on the trigonal bipyramidal. So how else could I do a trigonal bipyramidal? Well, I could take this fluorine and I could put it here. And then I can take this fluorine and I can put it here. So sort of like, let me draw it like this, where it's a bit clearer what I mean. So they're both equatorial, I guess you'd call it. Okay, so that's obviously equivalent to having that fluorine here or that fluorine here. So this is the preferred one, obviously, because we have our lone pairs are 120 degrees away from each other here, whereas here you sort of, it's difficult without drawing in the sort of the geometry. Let me just draw it in. You can see that these two lone pairs here are 90 degrees away from each other, and likewise here, because it's like that, they're going to be 90 degrees away from each other as well. So our linear structure is our easiest one. I feel like that's probably the 7 easiest marks on the paper right there. Although there were some pretty easy questions earlier on with the balancing equations. Anyway, then we have a rate equation question, and again, considering the kinds of rate equation questions they've asked in previous years, this one is really straightforward. So the following table shows the instantaneous reaction rates at 120 degrees for initial concentrations. Assume the reaction resistance is constant. What is the rate equation? So it's going to be rate equals K. So this, because we're assuming the reaction volume is constant, even though this is a number of moles, we can assume that it's basically a concentration. So it's going to be rate equals concentration of Xe, concentration of F2, and then we just need to work out what they are. So this is, you know, if this came up in an exam, like an A-level exam, you'd be laughing at how easy this one was, right? So here, Xe stays the same, here F2 doubles, and here nothing happens. So F2 is zero order. And then here, the F2 stays the same, the Xe doubles, and the rate doubles. So it's first order for Xe. So rate, I mean, you could just leave it like that if you wanted to. That, you know, you'd get the mark for that. I'm just going to make it a little bit simpler. K X E. All right. Lovely. Then we move on. Is it going to get any harder? Let's find out. The Arrhenius equation. Well, brilliant. The uncatalyzed reaction has a rate constant K, blah, 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 blah. And then, so here we go. This is the important part. The catalyzed reaction is 13 times faster at 120 and 23 times faster at 100, which is a little bit odd. So I guess, I mean, it's always faster, but the effectiveness of the catalyst seems to be inversely proportional to temperature. I don't know if that's a general case of catalysts. I don't know enough about catalysts, but it's like the higher. It's not saying that the higher it goes, it gets any slower. Obviously, the higher the temperature, the faster the reaction. It's just that the higher the temperature, the sort of the ratio, the effect of the catalyst diminishes. But anyway, that's beside the point. What we want is a expression for the ratio of the rate constants, which is a bit of a classic kind of question. Really, there's no real mystery here if you've thought about Arrhenius equations long enough. So I've got my K equals A e to the minus EA over RT. That's my uncatalyzed reaction. And then I've got K cat equals A cat e to the minus E cat over RT. Okay, so what we're doing is we're saying that obviously if I add a catalyst, I'm not going to change R because that's a constant. And if I add a catalyst, I'm not going to change temperature because to change temperature, I'd have to change the temperature. So the catalyst, what it will change is it will change your pre-exponential factor A and it will change your activation energy. And because those change, my rate constant changes. And all I want is just K cat divided by K. So it's just this divided by this, which is going to be very simply A cat over A, and then it's laws of powers, right? So it's your indices. So I'm doing this divided by this. So in other words, it's going to be, I wouldn't, obviously if I was doing the test, you know, under time conditions, I wouldn't write this out. It's e to the minus E cat over RT divided by e to the minus EA over RT, which is just this exponent minus this exponent. And because this is a negative exponent, it's going to become positive. So in other words, it becomes this exponent minus, or like plus that exponent. You'll see what I mean. It becomes e to the minus EA. No, I don't want the minus. Luckily, I've got this from the mistake earlier. Okay. EA over RT minus E cat over RT. Okay. So if you need to, just, you know, you can if you want, you can have this minus plus this, but then I've just switched it around, and then that becomes I'm going to factorize it because it says it wants it in terms of delta E. So I'm going to factorize it as A cat over A E to the 1 over RT EA minus E cat. And then you're told that delta E is EA minus E cat. So this becomes A cat over A E to the delta E over RT. Whoops, that doesn't make it any clearer at all. Oh, you know what I mean. All right, so again, only 1 mark for that, but fairly straightforward. This is a really common thing to be doing with our Arrhenius equations. So then, calculate the change in the activation energy, assuming that the collision frequency factors do not depend on temperature. So, what we've got is let's think. I know that at T equals 100 degrees C, K cat over K equals 23. And I know that T equals 120 degrees C, K cat over K equals 13. Okay, now what we need to do is it asks us to work out the change in the activation energy. So we're going to try and work out what this delta E here is. Now the problem is, so I've got, let me just write this out again. I know I've got K cat over K equals A cat over A E to the delta E over RT. So I know, let's say for this situation here, I know this value, K cat over K is 23. I know R. I know the temperature here. But what I don't know is I don't know this ratio here. I don't know what effect the catalyst has on the value of A. But what I do know is that when I change the temperature from 100 to 120, it has no effect on what this ratio is here. So that is going to be our sort of simultaneous equations, right? So what I've got, I'm going to make it clear to me, at this point, if you like the algebra, just do the algebra, right? To make it clear to me, I'm going to write out what my two equations are. So I've got 23, which is my K cat over K for this top one, equals A cat over A E to the delta E over, and I'm going to put in my T as well. So 273 is going to become 373. 373R. And then my second equation is 13 equals A cat over A E to the delta E over 393R. And now, so the reason I've done this is because like when I look at it, I know that R is definitely a constant, so I can ignore that. But now I can see my two unknowns. All right, so my two unknowns in these simultaneous equations are delta E and then this fraction here. So then all I need to do is just eliminate, and I'm going to eliminate this, obviously, because I know that that doesn't change. So if I do this top equation divided by this bottom equation, So if I do 23 divided by 13, that is going to cancel to 1 because that number doesn't change between the two temperatures. And then I get E, and I do this exponent minus this exponent. So it's going to be delta E over 373R minus delta E over 393R. In other words, 23 over 13 equals E to the delta E into 1 over 373R minus 1 over 393R. Now, like I said, you might find it easier just to do it all in terms of the algebraic variables. But for me now, you know, I know what R is, so all I need to do is just solve for E. So I'm going to run out of space, so let's go down here. It's going to be log 23 over 13 equals delta E 1 over 373R minus 1 over 393R. Okay, and then you can solve for delta E. So let's see if I can do that without making a mistake. Right. So what value does it want us to use for R? I've got R is 8.314, but my temperature is just 273 rather than 273 point something. Okay, so 8.314 is what we're using. So I'm going to do 373 times 8.314, 1 divided by that, minus 1 divided by 393 times 8.314. This could go wrong, couldn't it? Okay, so that's this that's in the brackets, and then it's just this number divided by that. So it's going to be log 23 divided by 13 divide by answer. Fingers crossed. Gives me that, which is the kind of number you want to see, right? Because when you divide it by 1,000, you're going to get a reasonable number in kilojoules per mole. Does it ask it in kilojoules per mole? Yeah, it says work it out in kilojoules per mole. Obviously, R 8.314. 8.314 is in joules. So we have to convert it to kilojoules by dividing it by 1,000. So this is going to give us 34767 joules per mole, which we're going to put down as, I'm going to put down as 35 kilojoules per mole. And then we can carry on. So next, again, I feel like that is a good 3 marks as well. You know, it's not. This is probably the kind of thing you might see in class, which is normal class, or at least like some similar sort of treatment. Then the rate determining step is this, and a more refined kinetic theory has this rate constant. So this looks confusing, but really, if you think about it, all it's saying is, in my Arrhenius equation, it's just saying that A is equal to beta T over mu to the power of a half. All right, so it's just, all this has done is just given us an expression for the collision frequency factor A, all right, the pre-exponential factor, which depends on temperature, depends on mass, and depends on some other constant beta. And then it says, determine the activation energy of this reaction using the data tabulated above. Okay, fine, not a problem. So I'm given values of T and values of K. Okay, so I've got T and I've got K. So you do the same thing. In fact, I could probably just ignore all of this stuff. Now that I've identified that K equals this, you know, I could write it out in those terms if I wanted to, but I don't think I would need to, because what's going to happen... No, I do need to. I do need to because it's got T in here. Now, I was thinking I could just do basically what I did earlier and just have this cancel between the two. But what I'm going to do is I'm going to choose two values. I'm going to choose this value, and I'm going to choose this value, the way you might do it in class is you might draw the graph and then take the gradient. But obviously you can just take any two, as long as these all lie in a straight line, which hopefully they will. I mean, the reason you draw the graph is because your experimental data won't necessarily lie on a straight line, right? So you might, the graph you should be familiar with plotting is log k against 1 over t, right? And you'll get these points. Okay. Now the reason you can't just take any two is because of the variation due to your experimental uncertainty, right? So you go through it and you take the gradient. But what we can do here is, because we're not doing any graph paper, we're just going to take two, and it makes sense to take the two that are furthest apart. Does it make sense? Yeah, because the closer they are, the more magnified any variation is going to be. Okay, so fingers crossed we've done a good job on these two. So let's do it. Okay, so not a huge amount of space. So I'm going to call this reaction number 1. I'm going to call this reaction number 2. And I'm going to write out K1 equals this one. I'm going to do a little bit more algebra before I put any numbers in. So the thing I'm changing between 1 and 2 is the temperature. Nothing else changes. Okay, e to the minus. And then also, when I change temperature, I don't change activation energy. So my activation energy stays the same, which might confuse you because earlier in the question we were changing activation energy, but earlier in the question we were dealing with a catalyst, and that will obviously change the activation energy. So now we've got K2 equals beta T2 over mu to the power of a half e to the minus EA over RT2. So those are my two equations. And then I'm just going to do the same thing again. I'm going to do this one divided by this one. So I'm going to do K1 over K2 equals, and then the betas will cancel. The square root mu's will cancel, and I'll get root T1 over root T2. And it's the same thing again. It's going to be E to this power minus this power. But because this is a negative, this one's going to become positive, and that one's going to stay negative. So I'm going to do it all in one step here. I'm going to go EA over RT2 minus EA over RT1. Okay, make sure you don't get that mixed up. All right, and then what am I trying to work out? Activation energy. So I'm going to have to do the log at some point. So let's just do the log now. So log K1 over K2 equals log root T1 over root T2 plus, and then the log of the exponential just gives me the whole thing, which I'll factorize out the activation energy and the R. So 1 over T2 minus 1 over T1. Okay, which should, if you practiced plotting this graph, this logarithmic form should be quite familiar to you now. Okay, obviously with a few things slightly different. And then I just go ahead and I put my numbers in. So I'm going to put in K1 is 1.55 times 10 to the power of minus 10. K2 is 2.07 times 10 to the minus 6. T1 is 50 plus 273, which is 323. And T2 is 273 plus 170. 373 plus 70. 443. 443. That's the hardest part for me. Okay, so then I put in all of those numbers and I solve for EA. I'm trying to think, do I want to do that? I want to rearrange it first. What's going to be quickest here? At this point you've got to choose whichever method's quickest for you, right? So let me think. Let's go EA 1 over T2 minus 1 over T1 equals R log K1 K2 minus log root t1 over root t2. Yeah, I think that's right. Yeah, and then so I can just work that out and then divide it by that. Okay, let's just try our best. Okay, so k1 divided by k2, 1.55 times 10 to the minus 10, divide by 2.07 times 10 to the minus 6, log that, gives me that. I'm not good at using these calculators. How do I want to do this? Let's just try and do it all in the calculator. Minus log root. Yeah. No, that's not going to work. Minus log. It's probably quite painful to watch. 323 divided by root 443. Jeez. Please be right. Did I know that right? Yeah, minus. Gives me that. Is that right? Times by 8.314. I mean, I'll know it's right because, you know, when the answer comes out at the end, it should be something sensible, right? Gives me that. And then I'm going to divide that by 1 divided by 443 minus 1 divided by 323. Fingers crossed. 92610. Okay, yeah, 5 digits. That's the kind of thing I want to see, right? So I'm going to get E. I can't believe that worked. 92610 joules per mole, which is. It doesn't ask for it in kilojoules per mole, but let's do it anyway. 92.6. Let's go 93 kilojoules per mole. Just trying to think, you know, so we've worked out this one was 35 and now this one is 93. Is that the kind of answer, you know, is there any way of knowing? Oh, it says here, the range for correct answer is strictly 92.4 to 93. Oh yeah, I had 92.6. Okay, so I'm fine. All right. So you do have to be within that range. I'm just trying to think if that makes sense, right? Because this is delta E, right? So that's the difference between the catalyzed and the uncatalyzed, right? So it makes sense, right? So it's saying that, you know, if that was my activation energy, then the activation energy of the catalyzed one would be 35 kilojoules per mole less than that. Okay, all right. Well, anyways, it's a sensible number. Okay. Then we have the final question. So, which is just a really bizarre question. It's a really nice question, but it just seems like they wanted it. I think they sort of maybe sat down and like, either someone had come up with this idea of a reduced mass question and really wanted to ask it, or they were like, can we add 2 more marks somewhere? But anyway, it says the reason is because of the way they word it, right? It has a relative mass of 128, which is mistakenly reported as 28 in the picture. So this is the picture they've got here. Now, it's a very strange picture. I don't know where it's from, but is it reported as 28? Maybe the one's hidden behind here. But anyway, they've obviously decided to go ahead with this. And so they're saying the current value of the mass of xenon is 131.29. How would the rate constant differ if it was actually 28? All right, so just for fun, right? There's no actual, reason it would be 28, except that that's what it says in the picture. And they give you the entire page. Okay, the entire page. So let's think. What we're saying is, I've got my actual 1 over mu, which is 1 over 131.29 plus 1 over 19. And then I've got my wrong 1 over mu, which is 1 over 28 plus 1 over 19. And it says, if I've got, assume all the other parameters are unchanged, I've got this equation. So I've got K equals beta T over mu to the power of a half e to the minus EA over RT. So it's saying beta stays the same. The temperature is given as 100. The activation energy stays the same. R stays the same, obviously, and temperature is 100. So the only thing that's changing is mu. And how does that affect the rate? Now it does say, oh no, it does say the rate constant. They could have said rate, and obviously the rate constant, okay, would be the same. So what we're doing is we're just changing 1 over mu from this to this, and we want to see how that affects this. Now, how that affects K. So, if you're really good at maths, this is not a problem. Okay, and they often, one of the recommendations they do say in the sort of the RSC Olympiad literature is, you know, if the students are good at maths, they should definitely just give it a go, because they can just, at this point, it's quite, if you're comfortable with it, it's quite obvious what you need to do, right? Basically, you just do the ratio. You do the ratio of these two and multiply it by your value of K. Okay, so you know, at 100 degrees, my value of K is 1.7. Okay, so it's going to be 1.7 times 10 to the minus 8 multiplied by, then I just do the ratio of the two, right? So it's going to be, well, the square root of the ratio, because it's the root, because this is 1 over mu, right? So it's going to be root 1 over 28 plus 1 over 19 divided by root 1 over 131.29 plus 1 over 19. Okay, so I just need to do that calculation. Let me, please see that I've got my calculator back out again. So 1 divided by 28 plus 1 divided by 19 square root gives me that. I'm just going to write it out. 0.29723. 1 divided by 131.29 plus 1 divided by, let's do 1 divided by 19. Gives me that square root. That. So then I do 0.29723 divided by that. Gives me that. Multiplied by 1.7 times 10 to the minus 8. Gives me, so my new value of K is 2.059 times 10 to the minus 8. Right, so if you see it, fantastic. If you don't see it, it's a little bit trickier, right? And I did think, you know, what could I, so let's take, the reason it's tricky to see what's going on, it's actually a very simple principle, but the reason it's tricky is because it's 1 divided by, and it's got a square root in it. So let's say, let's do a different example. Let's do F equals MA, which hopefully we're all completely familiar with. Now, if I have one particular mass with the same acceleration, that gives me one particular force. And then if I change my mass to M2, but I want the same acceleration, I'm going to require a different size force. Okay. Now the question is what's the effect of the mass on the force? So it should be fairly okay for you to see that in order to work out F2, all I really need to do is M2 divided by M1 multiplied by F1. Okay, so the ratio of this mass to this mass multiplied by that force is my new force. I guess I could have chosen a chemistry example, right? Because this is obviously just the same thing as C1V1 equals C2V2, right? Where your new concentration is your old concentration multiplied by the ratio of the volumes, V1 over V2, okay? And that's all I'm doing, right? So it's the old force multiplied by the ratio of masses, it's the old concentration multiplied by the ratio of the volumes. Here, it's the old rate constant multiplied by the ratio of the square root 1 over mu's. That's all I've done. Okay, it's the new term divided by the old term multiplied by the old constant. If you wanted to do it algebraically, let me think. Could you do it algebraically? Could you say k new divided by k old? I haven't tested this. Beta is going to stay the same. So yeah, so if I divide them, then the beta divides, the t to the power of a half divides to give you 1. So then I get square root 1 over mu new divided by square root 1 over mu old e to the minus ea over rt divided by e to the minus ea over... Yeah, okay, so you can do it like that. That was probably would have made more sense to do it like that from the start. You know, so if you were to write out what I've done, I should have planned this a little bit more carefully. I've got my new k is equal to... But it says, because it says that everything stays the same, right? So beta, root t, root mu, e to the minus ea over rt, and k old equals beta, this is the new one, root t, root mu, old, e to the minus ea over rt. If I do this divided by this, that cancels, all of that cancels. So all I get is just this equation here. Okay, now, if you get it, obviously you probably stopped watching this about 15 minutes ago. If you don't get it, you know, work through the maths a little bit. It should be fairly achievable. But I feel like that's a very nice rate question. They could have asked a much more difficult rate question. 2 marks for that, I feel, is fair. Although I feel like 3 marks for both of these. 3 marks for that and 3 marks for that. I guess there's nothing too difficult here. It's just whether or not you can see what you need to do. But anyway, 2021, great paper. Hope you enjoyed it.